Hello everyone, my name is Dr. Diaz and I'm a chemical engineer and also environment engineer with an academic journal that includes an MBA, Master and a PhD in environment engineering. My work bridges the worlds of industrial innovation and environmental responsibility with a deep focus on waste valorization bioenergy, a topic I truly love and have dedicated much of my career to. Back in Portugal, I had the privilege of teaching biotechnology course, petroleum technology, and leading projects in this field, which gave me first-hand insight in both the power and environmental costs of fossil fuels. Today, I'm committed to exploring and promoting sustainable alternatives. If you want to minimize the negative environmental impact of fossil fuels use and the growing volume of waste, one of the most promising solutions is to valorize waste, transforming into renewable fuels and a valuable resource. Bioenergy is not just a technical solution. It's a pathway toward a cleaner, more resilient future, and I'm excited to share insights, strategies, and innovation that can help us move from waste to worth. And probably you're asking yourself why I'm talking about energy and bioenergy. First, let's start with the energy. We know that energy is important for the progress. And energy powers everything: homes, transportation, industry, agriculture, communications. Without energy, modern life, healthcare, education, and innovation would stall. It's essential for clean water, food production, and emergency response. But until today, reports from various sources indicated that the global economy remains heavily reliant on fossil fuels. Fossil fuels currently meet approximately 80% of the world's energy demand. Energy dependence and independence, like in 2023, the United States imported about 8.51 million barrels per day of petroleum from 86 countries. Crude oil imports of about 6.48 million barrels per day accounted for 76% of United States total gross petroleum import. And why I'm saying that? Because it's important to remember that one of the most important things for a country is to be independent, like energy independent. And I will tell you why in the second slide. Another driving force is the pollution due to extraction and excessive and increasing use of fossil fuels. Another is the greenhouse effect, global warming, among others like climate change, right? Remember that I said I'm going to talk about this later. So why is important to be highly independent and energy? So we had in the past in 1976, in this period of time, we had the oil craze that came with the pro-alcohol. So some countries struggle with the scarcity of petroleum and the high prices, so they start develop the alternative fuels, like Brazil in South America. They start producing the alcohol, so they call the crazes the pro-alcohol crazes, because it came with the oil crazes. We have wars, we have economic crises, and that shows the fact and the price of the petroleum. You can see here in 2008 the global financial collapses, so the price of petroleum went really up, so high prices. So invest in bioenergy is not only sustainability, it's not only to prevent the impact on environmental. It's a smart movie. Sustainability meets the innovation. So the driving force here would be the climate change mitigation, like carbon neutrality, reduce greenhouse gas emissions, meet climate targets, getting find the independence, energy independence, security. So reduce the dependence of fossil fuels import, diversification of energy source, economic development, rural development creates green jobs, small and medium-sized enterprises, and also the environment benefits like waste valorization, circular economy, reduction in greenhouse gas emissions, lower air and water pollution, sustainable land use, energy recovery. And of course, we have some solutions like renewable energy, like solar panels, wind turbines, geothermal power plants, hydropower. These are crucial, but not enough alone to meet global energy demand or emission goals. It's important as well to remember that all the process can generate an impact. So that means that doesn't mean that if you're producing bioenergy or trying to uh, minimize the impact of environment with the use of fossil fuels, but if you're using like fossil fuels to producing bioenergy, so that doesn't make any sense. And sometimes you're doing everything right, however you are creating another impact. This is why we always have some studying everything, like the background study and everything that we do. Like here in the solar panels, like the floating solar photovoltaic system, and at UCF they have a study, a research to monitor the performance, durability, water quality, impact, and the biodiversity interaction for existing floating solar sites across diverse climate regions. So it's important because sometimes we think that that is a good step. That's a good way to produce renewable energy, but then we are creating another impact. So this is why those results are really valuable. So besides the renewable energy, we have the bioenergy that it's also renewable, but not all renewable energy is bioenergy. Okay, so because renewable energy encompasses a broader range of sources like solar, wind, geothermal, which don't rely on organic matter as the bioenergy. Okay, so unlike solar wind energy, bioenergy is storable, dispatchable, and compatible with infrastructure, support rural economies, agriculture diversification, and waste valorization. Here is a case of waste valorization. It's one of my research. So here, this is me with the microalgae. In the back, we have a waste from industry. That's the grape bagasse that we use as the nutrient source to grow microalgae. And also, that is a case of waste valorization, that we can use those microalgae not only to produce bioenergy, but it could be used to produce protein as well, not only bioenergy. So bioenergy is a form of renewable energy derived from biomass. And what is biomass, right? So biomass is defined as organic material derived from plants and animals, agriculture waste, algae, and more to generate fuel and electricity. It also can be defined as any organic material or waste that contains chemical building blocks like hydrogen and other carbon and other components that are vital to our modern energy and materials economy, like carbon, hydrogen, and how they work. So biomass is the single largest supply of carbon on the planet Earth, and is a sustainable and renewable source for the products that are currently made from petroleum. Here's how it works. We have photosynthesis, right? So trees and plants, like here, will absorb the sun through the photosynthesis, which is a complex process that involves the plant using energy from sunlight to combine carbon dioxide with water to produce sugar. So the energy is trapped inside until the organic material is converted into other products that are used as source of energy and materials. Biomass contains carbon absorbed by plants through the photosynthesis. When the biomass is used to produce energy, the carbon will be released during combustion and return to the atmosphere, making modern bioenergy a low emission fuel. So, and we call biogenic carbon dioxide over here. So that originates from recently living or almost living organic matter harder than fossil fuels that we can see here. So this CO2 here and the carbon zero cycle over here is part of a natural, relatively short-term carbon cycle. So the same, we have the plants that will absorb this biogenic CO2 and they use during the photosynthesis to produce sugar, right? So these plants will absorb and then we're gonna use again and then we're gonna burn and send back to the atmosphere. That is a cycle and sustainable cycle. The fossil fuels will not happen there, so no biogenic CO2 will emit to the atmosphere, but we don't have plants to absorb that. So the fossil fuels will not absorb the CO2 produced. Okay, that's why we have carbon free for the bioenergy sources. Okay, so there are several kinds of biomass such as agricultural residuals, purpose grown energy crops. Biomass also includes waste, and there are processes that work for many types of waste biomass like animal waste. That's right, like poopy. Believe it or not, poopy can be used to make electricity, manure from farm animals, mostly cows. It's put in a big tank called a digester, and we're gonna talk a little bit about that in few slides. Methane can also be captured in landfills, and we're gonna talk as well about this. So here we have a sample of other types of biomass like used cooking oils. Here we have the agriculture that we can produce biodiesel from those waste over here. Agro-industrial waste over here in the back. Also over here, like the crop residuals, and we have the forest lignocellulosic biomass, wood processing residuals. This is in my last project that I was working with. And here, time to think a little bit. So I will ask you to stop the video and think about this question. Does any biomass is useful for producing bioenergy? So can I use any of the types that I told you, I gave you as an example, or if I'm looking through my windows and at this moment I'm looking at a tree outside and I can see the birds are eating the seeds over there. So, and that is something that we humans don't eat, but the animals are eating. So probably we have some sugars over there, and do you think I can produce ethanol of that? So does any biomass suitable for producing bioenergy? Think a little bit. Those leaves that is coming down, do you think that you can grab that and produce energy with that? Okay, so no, the success of the biofuel and bioenergy industry depends on the quality and the quantity of biomass available, in addition to the cost effectiveness in terms of production and usage. So we depend on the physical characteristics like humidity, granulometry, and density, chemical characteristics like energy properties, rheological properties like elastic, cohesive. So the sustainability would depend the type of energy, technology available, economic sustainability, and environment sustainability. So when you talk about the sustainability aspect, so we take in consideration several things, like greenhouse gas emissions, while often considered low carbon or carbon neutral alternative. The actual greenhouse gas emissions of bioenergy depend on factors like biomass type, land use, and the conversion efficiency. Life cycle assessment is crucial for accurately evaluating the full greenhouse gas footprint of various bioenergy pathways. Consider factors like direct and indirect land use changes, The land use, large-scale bioenergy development raise concerns about competition of food production, deforestation, habitat loss, and soil degradation. Sustainable land management practices, utilizing marginal lands and focus on second-generation biofuels from no-food feedstocks can mitigate these risks. Water usage, concern about air and water pollutions. So, and also in economic sustainability, we need to think about the cost and competitiveness. So, bioenergy can be more expensive than fossil fuels. Bioenergy production can create jobs. That's a good part, and stimulate economic activities, especially in rural areas. Okay, so this is all that we can think about it, like technology innovation. While first generation biofuels utilize well-established technology, advanced biofuels like cellulosic, ethanol, biomass-based aviation fuels, other novel bioenergy technologies face challenges related to scalability, energy efficiency, and cost effectiveness. Okay, so for hundreds of thousands of years, humans have used wood or charcoal made from wood for fuels of heat homes, right? And cook food. To make bioenergy from wood, scraps or sawdust can be collected from farms and forest manufacturers. There are several ways to convert biomass into usable energy, and it can be even be turned into fuels to power cars. And I can see like with driving a car moved by wood, and trucks and airplanes. So the technology I'm talking about is biochemical conversions, physical chemical conversions, and thermal conversions. I'm here talking the main process that we use it. Like in the biochemical conversion, we have anaerobic digestion. Remember the poopy from cows that I said? We can use anaerobic digestion. And we have fermentation, like to produce ethanol, for example. And we have physical chemical conversion, that is transesterification, for example, that we can use to produce biodiesel. And the thermal conversion have the combustion, the most old process that we have. So we can produce heat, and through the heat we can produce electricity. We have the gasification, pyrolysis, and liquefaction. Pyrolysis and liquefaction will produce gas, oil, and coal. Here we have some example that I think it's pretty good. And it shows how outside countries, other countries, and even here they're investing as well in this area in the United States. And actually, United States is worried too about use their own waste and resources to produce the bioenergy, which is really good idea. And here we have an example of MBT plants. Here we have two. So this is me and my students over here. And what they do is treat waste like urban waste. So they have the mechanical treatment that will separate the waste, so they can recover some recyclables and the usable materials, and then they can send this waste like in the anaerobic digestion. So in the process, they will produce biogas. And also they can produce compost, like rich in nutrients to correct soils. And here we have an incinerator that is work with the combustions to burn waste, and they produce heat and electricity as well. So here in the back they have a power plant, so they treat the gas produces and also produce energy. And here we have a project that it's really funny because that is the thing about cows, like they burp, right? And the only difference between us is bovine burps are a big problem for climate change. The burp is combined with the less frequent bursts of fluctuation are a side effect of cattle digestion, and they are responsible for more than 20% of the nation's heat-trapping methane gas emissions. So that's 2 times as much methane as the United States oil and gas industry produce. So here it's a project in Argentina. So you can see the cone with the backpack here. And actually this is a bag that collects the gas inside. Don't worry, this is a painless. So the cow is not suffering. They are well. You can see it. She looks well here. But the gas is trapped inside of those bags, and they treat the gas, and they can have cars moved by methane on those places. Not only then, but MBT plants as well. So they produce biogas and they can use that. So they can use also the manure of those areas, like, because remember the poop from cow is powerful, so we can send this to biodigester, so we'll stabilize this organic matter, and then we'll produce a gas. This biogas can be used to produce energy. Also, we can have biogas in landfills. So here we can see a part of the landfill. So these tubes over here are to capture the gas, and we have the biogas treatment installation over here. Of course, we have the leachate over here as well. All can be treatable, and the biogas is not the same quantity that we can produce here and biodigester, because this is more controllable, so we can control better the process. So biogas and natural gas have the same formation process, but don't get it confused. Biogas is renewable energy and natural gas is a fossil fuel energy. So here you have image of landfill. That's a pretty new landfill in the back, and here we have the installation to capture the gas, treat the gas, and produce electricity as well. So the anaerobic digestion is important. We can use the methane to fill the cars. Here there's trucks that source is from Scania, and they are moved by biogas, so methane. So this is why we have here, this is in Italy, so they have methanol. So that's methane produced in MBT plants, mechanical biological treatment plants. The American Biogas Council has released a new data showing in 2024 another record, like 125 new biogas projects came online, representing over 3 billions in new American investments. The biogas production here in the United States, so 72% come from landfill, and we have 13% from agriculture, wastewater 12%, 3% is from standalone food waste. So we have the biochemical conversions. So here in this case we have the fermentation. So alcoholic fermentation is the action of yeast, usually unicellular fungi of the species Saccharomyces cerevisiae, on fermentable sugar containing a solution suspension. Fermentation is a biological process in which the energy generated by oxidation reactions and can be used for yeast growth and anaerobic partial oxidation of the D-glucose used to produce alcohol and CO2. Here is it's a fermentation in a bottle happening over here. So you cannot see, but it's very insulated bottle because they are producing a lot of biogas, and that was organic matter. It's not actually sugar inside, it's just waste. Treatable, like the waste was treated before the fermentation. The people have no idea how uh, hard is the process. Like everybody thinks that it's a really easy process, and actually, if you use the sugar cane, that will be more easy. But when you work with the waste, here is a very simple example. Here is an example of waste chosen by the students that I had during summer in Portugal. So these students chose orange peel to produce bioethanol. So first thing, they had to collect the orange peel, and they went to restaurants to collect it, and then they had the physical treatment, chemical and thermal treatment, and then they analyzed the sugar contained on those orange peels. Then they passed through the fermentation process, and here the students analyzing the fungi, if they are alive or not. They love this part because most of the fungi, part of the fungi die with the alcohol, so they produce alcohol and then they die. So here we have the distillation process, and here is the final test. They burn the alcohol to show we have alcohol here. So the challenge in this process now is stop to use food and they use food crops. So lignocellulose biomass, like crop residuals, wood chips, and the grass, it's a promising but a very complex. This is the waste that I was using. This is lignocellulose biomass, and this is waste from corn. And here I'm analyzing some samples. The challenge lies in the pre-treatment, like breaking down the structure of cellulose, hemicellulose, and lignin to access fermentable sugar is not easy. We need to prevent the use of energy like a high temperature or use of expensive enzymes to cut down those cellulose. However, we are getting there, right? So we use, like today we can find enzymes with not so high price and they are very efficient. They're used in traditional microbes struggle to, because they know that some traditionals will struggle with all the sugar efficiently. However, there are some researches going on that promise a good fungi that will produce ethanol and a very high percent yield, because they are more resistant to ethanol than the other fungi that we have. Another problem is the variability in the feedstock. It's hard to get the same type from the beginning up to the end. And then we have also the steps of purification, distillation, that will add more cost in this process. So how we could make this more sustainable? If you create a project, a process that is in context with the biorefinery, that will be more sustainable. What is the refinery? So the refinery will not produce only diesel or gasoline in a fossil fuel refinery. For example, they produce heat, and then through the heat they produce energy, and they produce fuels and the chemical compound as well. So the same thing we can do with the bioenergy. So we can create biorefinery. Instead oil, we're gonna use biomass. So, and fossil fuels, they will produce CO2, but that is not carbon free like a biorefinery that will be absorbed by the plants that was used to produce the biofuel. Another process is the transesterification. When you talk about transesterification, the first thing that comes in my head is the biodiesel. Which what happened here in the transesterification process? We have the fats or oils, like triglycerides over here. So we see that we have the acid functional group over here. Then we react with alcohol. Okay, so it can be ethanol, can be methanol. And then during this reaction, I have a catalyst over here. We're going to produce a glycerol and an ester that will be used as a biodiesel. Okay, so the glycerol is a subproduct that, depending on the company, will valorize this and sell this product. So we can have money from glycerol and ester. Sometimes some companies think that it's not worth to treat the glycerol produced to sell a better price, so they sell this low price, but it's still a subproduct that has some value aggregate on that. Okay, so but you can ask, so okay, so they use the oils, or they can use clean oil. To use a clean oil, virgin oil, so you're competing with the food system. So you need to think about the food security, because thinking like this, if I am agriculture, so I have soy, so I sell my soy for a good price, but then come people from industry that produce biodiesel and ask me like, can you sell this to me? I'm gonna pay you double. What happened here? Do you think the agriculture gonna think about okay, so I will not sell this to produce food, I will sell this to produce biodiesel because they're gonna get more money, like double. So of course they will sell for more money, most of them. So, and I'm not telling that you all gonna do the same thing, but the risk to this happen is high. So the goal here is to use the cooking oils and then to produce the biofuels. So then you can ask, is the quantity enough? So how is the quality? So the quantity to be enough, then here comes the dependence of another country. So in Portugal they import from other countries, but they have the collecting point system and also the door-to-door collecting. So you can see here they give you like some bottles, so you can fill it out, then you put inside of those little stores, banks, and then you grab another new bottle, so you can fill it out again when you use oil. Okay, or we have this type as well, so you don't need the bottle, so you put it inside, you dispose the oil inside of those kind of trash can over here. But this is not so much sustainable because they need to clean most of the times, because the people spells and you have oil for all outside, so it's not a good idea. So this is a better idea. Of course you're producing waste as well, but the bottles here are reusable, so they wash back and put it back over there. So we today, in a long time, we have the biodiesel blended with the diesel. So we have the B5 and the B20. So B5 is 5% biodiesel blended with the diesel, and the B20 is between 6 to 20% of biodiesel blend over there. The production is increasing, and not only in the United States, but in most of the countries. Europe is more stable since 2018-19, but the other countries are increasing like very well over here. Okay, so biodiesel has reached a record level worldwide according to the International Grain Council, that report by German Union for the Promotion of Plants. The increase in production was driven by growing soybean production in the United States and South America. This is what it says on the last report in 2024. So based on the official data, private sources and forecasts, estimated the global 2022 production of biodiesel, including hydrotreated vegetable oil (HVO), reached a record high. Let me just get back over here. A high of 71.5 million tons. This would be an 11% increase of the previous years and almost exclusively based on increasing in North America and South America and Asia. So here you can see the biodiesel United States. So you see here in 2024 a very large increasing over here as the renewable diesel, which is the HVO. Of course, the used oils, we have a high heterogeneity, high content and water, and also in fat-free acids, and most of the times the oil comes with a high sulfur content. This is a problem, and I had worked on this for several years at a huge company in Portugal, and also Dr. Huyali worked with us in this, and we have an article published in this area in a conference. So, and the thermal conversion, so now let's talk a little bit about thermal conversions. We have the combustion, which consists of the chemical reactions between two or more reactants, fuse and oxidizer, a large release of energy in form of heat. So we have the heating in the process. So this is a very, here is still endothermic because they need to absorb energy here. So we have the drying between 100 and 150 degrees. And then we have the pyrolytic decomposition. So here in this part, the long chain components of solid fuels will be broken down into short chain compounds, producing carbon monoxide and gas hydrocarbons over here. And then we have the gasification of water-less fuel, and then the gasification of solid carbon, and then oxidation of combustible gas, approximately between 700 degrees Celsius and 1400 degrees Celsius. And then we're going to have a very exothermic reaction, so combustions, we're going to produce heat and light, and with this we can warm water, we can produce steam, and we can produce electricity as well. The main combustion equipment, so we have the gas turbine combustion chambers, ovens, boilers, incinerators. The ones that is more popular is the boiler with great combustion, which is a classic and widely used system for burning solid fuels like coal, biomass, wood, and including waste. Is really relevant in industrial and municipal settings where fuel flexibility and robust operation are key. So creating combustion. So here are the key components. So the grate over here, you can see the grate is acting as support platform and allows air to flow inside. So you can see here the air is a full bath of here. So we have the fuel, so we have the primary air, so we have the grate over here. So the grate surface is made of cast iron or steel bars and holds the fuel and allows ashes to fall through. So you have another one to show you. So but here it's better to see it because in the air supply system controls primary and secondary air for complete combustion. And so we have here the waste coming, right? The solids come in. So combustion chamber where volatile gas are fixed carbon burn in stages. So that is another thing. It's easy to remove the ashes, so we have manual or mechanical, depending on the grade type. Okay, so in this type of combustion, as used in many places, so we have some pollutants, of course, resulting from incomplete combustion, which is carbon monoxide. We have carbon, hydrocarbons, and tar compounds, unborn particulate, and we have pollutants results from complete combustions, with nitrogen oxides and residual carbon monoxide. So besides combustion, we have the pyrolysis, which is a thermochemical decomposition process that breaks down organic materials at high temperature in the absence of oxygen. Here we don't burn, okay? So here it's a process that we're gonna produce a biochar that normally is used to correct soil. So that is also used as filtration material to clean up wastewater, or as I said, used as corrective for soil, so they will be returned to soil conditioner to improve the chemical and physical and the biological properties. Also, we can produce biofuels and syngas. So, slow pyrolysis occurs at a temperature of approximately 400 degrees, and this final product is charcoal, and also call it biochar. And we have also the fast pyrolysis that we're going to produce the bio oil over here. So it's a thermochemical process that rapidly heats biomass. So in the absence of oxygen, I said that in the pyrolysis we don't have oxygen, okay? And they will produce bio oil, biochar, and gas. It's a method for convert biomass in valuable liquids, fuels, and other products. The process involves quickly heating biomass to around 500 degrees, followed by rapid cooling to condense resulting vapors into bio oil. Incredible process, I love it. And another process that is very important here in terms of thermal process is the Fischer-Tropsch process. It's a fascinating and powerful chemical technology that transforms syngas. Remember, syngas produced via and pyrolysis. That is a mixture of carbon monoxide and hydrogen in liquids hydrocarbon like diesel, jet fuel, and waxes. It's a cornerstone of gas to liquid and biomass to liquid fuel production, especially relevant in sustainable energy and synthetic fuel development. So these produce mostly alkanes, which are ideal for clean burning fuels like low sulfur diesel. The challenge here is for traditional fission-Tropsch reactors like slurry bed, fixed bed, is the hotspot from exothermic reaction, and we have the catalyst fouling, pool heat transfer, and also we know that all the process has a challenge, right? But the challenges are there to be solved, and they solve the problem with the modern microchannel reactors. They solve this by using thousands of tiny flow channels to improve heat and mass transfer, making Fischer-Tropsch more efficient and scalable. In the real world, Fischer-Tropsch fuels are already being used in aviation. In fact, synthetic paraffinic kerosene produced via Fischer-Tropsch has produced like with conventional jet fuels for transatlantic flights, showing its readiness for commercial deployment. So HVO is another biofuel. It's not biodiesel, but it's also produced with vegetable oils. It's actually hydrotreating of vegetable oils. It's a modern way to produce very high quality bio-based diesel fuels without promising fuel logistic, engines, exhaust, after treatment devices, or exhaust emissions. Um, why this is different from the biodiesel if they are produced from the vegetable oils? Can you think about it? Can you tell me the difference between HVO, that also called as renewable diesel fuels instead of biodiesel? Why they are different? 5 minutes, or stop your video and think about it. Why HVO? What is hydrotreating says over there? Okay, HVO is a process where hydrogen is used to remove oxygen from triglycerides. So we're gonna remove all the oxygen and triglycerides, so we're gonna have esters at the end, and we will not produce glycerol as a byproduct. Additional chemicals such as methanol for flame production are not required as well over here. Okay, so hydrogenation removes all oxygen from vegetable oils, while transesterification does not. So that is the main difference between HVO and biodiesel. If you look at this table, we have the density of HVO. We have, let's focus on the vegetable oil here, both HVO, and we have also the FAME, which is the biodiesel. Okay, so if you look at the density, FAME is denser than HVO. Viscosity also, FAME has high viscosity compared to HVO. We have more cetane number, 80 to 90%, like 9, while the FAME has 51 cetane number. It's not percentage, I'm sorry, I said percentage. Distillation range, so 180 degrees Celsius to 320 for HVO, while FAME is 350 to 370. Cloud point is pretty close. Heating value is also close, it's not too different, and heating value lower as well. In megajoules per liter, no, is almost the same. So they don't have aromatic, so polyaromatic as well. But oxygen content, HVO has not oxygen content. Sulfur content is very low, and storage stability. Biodiesel is very challenging because we have oxygen in it, so we suffer oxidation. So we normally wait on storage for more than 6 months. So if you have a car moved only by biodiesel, and if you go to another country to study and get back 1 year later, you're gonna throw away your biodiesel, okay, because that will not last forever. So here another table, so that I compare Fischer-Tropsch, hydrotreating, and esterification. So esterification is the biodiesel, and the volume available in the prices, so you can see the Fischer-Tropsch is better compared to those esterification, hydrotreating. The product quality, hydrotreating, which is the HVO, and Fischer-Tropsch, is much better than esterification, so the biodiesel. And the investment, planned investment is really high, and it's a benefit for esterification, and it's not a benefit, it's a disadvantage to HVO and Fischer-Tropsch, because they are very high cost plants. Okay, so I know this is a short time to talk about everything, so I tried in this point to show you the most important process and what is happening in the world, and but we cannot forget how they divide and classify the type of biofuels that we produce. We have the first generation biofuels, that is conventional biofuels that they use food crops to produce biofuels such as sugar, starch, and vegetable oils. But this has a big problem because it's competing with the food, right? So we need to pay attention to food safety. Like in this cartoon over here that says, no, but I can offer you a gallon of ethanol. So why this happens? Remember that I said about what I talk about the soy. So imagine if I have a corn or sugar cane, area field of that, and I use cell to produce food. But some people from industry come like, okay, can you sell for me? I'm gonna produce ethanol, and they offer me a double. Probably gonna sell for them for double, right? Then the part that we're gonna sell for food, we're gonna have a very high cost because now we're gonna have a small part to sell for food sector, and so the price will increase. So this is why it's a problem to compete with the food area. Okay, so of course, on the other side, those technologies, fermentation to ethanol, transesterification to biodiesel, it's well developed technology, so easy to implement. The big advantage here is that competes with food production and environment concern with the land use. They have the second generation, which are the biodiesel or advanced biodiesel produced from lignin cellulosic biomass, such as wheat, straw, wood, grass, including agro-industrial and forestry waste, municipal and agro-industrial waste, non-food crops. This photos is all mine. So from my project, we always try to find a new solution, a new way to produce the bioethanol or biodiesel in a very cost-effective way. But the technology like enzymatic hydrolysis, gasification, fermentation, transesterification, anaerobic digestion, so we still have a very high complexity processing, mainly because the pre-treatment with the high cost with the enzymes and the other treatment process can be the steam explosion, which is really a high cost as well. So the advantage here is the less competition with food and the sustainability in terms of environmental, but in cost it is still high. It's really hard to compete with the fossil fuel price and the ethanol produced of the first generation price. And we have the third generation that we use biofuel from marine biomass and algae. So we can produce biodiesel, biogas, and hydrogen. So the advantage here is a high yield per area. See here I have a microalgae sample, and we can produce a bunch of microalgae in a very small area, while to produce a soy you're gonna need a very huge land to produce. Okay? But the challenge here is expensive to cultivate and process. This is why my project we use, that's not my project, I work in this project with my colleague. It's her project, and we use the waste from industry. So that is a grape waste, so bagasse, that's a grape bagasse that we use part of this as a nutrient. It's not full of only grape, but it's part to the nutrient used to grow microalgae, which is very sustainable. Right? So, and we have the fourth generation, which is advanced and combines cutting-edge technologies like synthetic biology, genetic engineering, and focus on maximizing yield and efficient and sustainability. Okay? So when you talk about the genetic metabolic engineering, like microorganisms that are engineered to optimize their metabolic pathways, making them efficient cell factories for direct solar to fuel conversion, for example. Despite the high costs, like advancements, the costs associated with cultivating and processing genetic modified biomass for large-scale biofuels just remain high, according to scientists directly. So it's really high. During this class, you could see that we have different types of conversion process, different type of biomass, but you learn that not all the biomass can be used to produce bioenergy because they need to be sustainable. We need quantity, we need availability, need to be close as well, because if you're gonna spend gas or produce pollution, emissions, and everything, like just to transportation, your process start to be unsustainable, right? So if you use fossil fuels like coal or natural gas to power bioenergy facilities, this undermines the carbon savings. If you generate hazardous waste or toxic byproducts during processing, especially in chemical pretreatment or catalytic recovery, that is unsustainable. If you use excessive transportation and they have excessive transportation emissions, if feedstocks are shipped at a long distance, that is unsustainable. So you could see and could hear from me that we can produce biogas from animal waste, right? So you can go to the biodigester and produce biogas, and you can use it to have some countries that already have trucks moved by methane. We have digestion, we have the landfill gas, we have fermentations, we have incinerators, we have fissiotropisch, we have several processes to produce bioenergy. The goal is always to find the most sustainable way to produce those bioenergy. When you talk about sustainability, we talk about economic sustainability, environmental sustainability, and our social sustainability. Okay? So the challenges here is policy uncertainties, so financial barriers or high capital costs, fossil fuel subsidies, and limited access to affordable finance mechanisms. Complex regulatory frameworks and change mandates create investment risk. Advanced biofuels for aviation, industrial heat application requires further development, and feedstock variability, logistic challenge, and sustainability certification is not making the bioenergy life easier. Of course, we have a legislation that driving bioenergy research and productions, like the Renewable Fuel Standard, that establish annual volumetric requirement for renewable fuels for transportation sector, driving demand for conventional and advanced biofuels. We have the Energy Independence and Secure Act that set targets of 36 billion gallons for renewable fuels by 2020, including 16 billion gallons from cellulosic biofuels. And we have Sustainable Aviation Fuel Grand Challenge. The target is 35 billion gallons per year of sustainable aviation fuel production by 2050. We have different types, as you saw over there. Conventional biofuels, they are any fuels derived from starch feedstocks. Conventional biofuels produced in plants built after 2000 must demonstrate a 20% reduction in life cycle of greenhouse emissions. And the advanced biofuels, I'm telling this because it's over here in renewable fuel standard. Any fuel derived from cellulose or advanced feedstock. This may include sugarcane or sugar beet based fuels, biodiesel made from vegetable oil or waste grease, renewable diesel, co-processed with petroleum, and other biofuels that may exist in the future. Biomass-based diesel and the cellulosic biofuels. Biomass-based diesel is a fuel substitute made from renewable feedstock, including biodiesel and non-ester renewable diesel. Fuels and category must demonstrate life cycle greenhouse gas emissions reductions of 50%. And cellulosic biofuels, like any fuel derived from cellulose, hemicellulose, or lignin, non-food based, like renewable feedstock. And fuels in this category must demonstrate life cycle greenhouse gas emissions reduction of at least 60%. Recent studies and trends in bioenergy. So 23.8 billion US biofuel capacity. So per year in 2023, with renewable diesel growing most rapidly. 50% energy growth by 2050, while with bioenergy playing a crucial transitional role. 5 key barriers. IRENA, International Renewable Energy Agency, identify 5 critical barriers over here. Policy uncertainty, financing gaps, technological readiness, supply chain issues, and awareness. Recent research emphasized the importance of innovative feedstock like agricultural waste and lignin-cellulose biomass that avoid competition food production while careful account for life cycle emissions and land use impacts. I would like to talk a little bit about my projects here, biodiesel and bioethanol innovations. Biodiesel from waste cooking oil, reducing the sulfur content. And this, I work with a Prior Industry, which is the third biggest producer in biodiesel in Europe. And also Dr. Hu Yangali participated in our article. They contribute there. So we work together on this. So that is circular economy approach to waste valorization, significant greenhouse gas emission reductions, and the process optimization for improved yield and quality. The other project that I have is bioethanol from lignocellulosic biomass, which I'm trying so bad to bring to Florida, this project. So advanced non-food competing feedstock utilization, enzymatic and chemical pretreatment innovation, and fermentation processing enhancement. Here we have some used cook oil, and the biodiesel here is in the back. This is me, and Stacks. Stacks it's a company that creates startup for bioethanol productions, like in the concept of biorefinery. This is the biomass that I was using, lignocellulosic biomass. It's a wood, from wood. It's a waste from paper industry, actually. And here are some samples that I was analyzing in the lab. So the advantages of the bioenergy. So we have a renewable resource derived from widely available organic materials, including forest residuals, agricultural waste, and dedicated energy crops. Waste reduction, so we valorize organic residuals, reducing landfill methane emissions and creating value from waste streams. Reliable energy provides dispatchable power, like intermittent solar or wind, ensure consistent energy availability. Bioenergy enhances energy security, diversifies energy supply, supports rural economies, and offer significant potential for greenhouse gas emission reductions compared to fossil fuels when the source sustainable. So diverse energy is equal resilient future We need a diverse energy portfolio: solar, wind, nuclear, and bioenergy. Bioenergy is the bridge to a low carbon, more inclusive energy. Let's rethink waste, rethink fuel, and power, progress, sustainability. This is important. And remember, not all the biomass can be used to produce bioenergy, and not all bioenergy is economically sustainable. If you want to produce sustainable bioenergy, we need to follow the same steps of the oil refinery. So we need to work in the concept of biorefinery. So not only produce a biofuel, but also produce other chemical compounds with value aggregates, so that can be sustainable, and then we can also take advantage of all the resources that waste can give it to us. Okay, that's it. That's all. Bye for now.